That said, let us show the slides. Here are the slides. Right, and first of all, we have our first definition of what it means to compute a real function. Let us recall that. To compute a real function means this is a perspective of a function as a transformation. So there's a real number argument and a real number return value. And what it means to compute the return value, this is our usual definition, which you can see on the bottom of the screen for your convenience. Namely to output approximations up to arbitrary error 2 to the minus n to that real value. So suppose or consider the real number r here replaced with the value f of x of that function f here, and approximating by, let's say, rational numbers, or which is equivalent, as you recall, by dyadic approximations, that is by fractions where the denominator is an integer power of 2 and the numerator is another integer. So that's what it means to output the value of f of x. But of course, the new thing and the subtlety about computing real functions is that now, for the first time in this lecture, also there is a kind of infinite input, namely a real number argument that somehow has to be fed, that has to be presented, that has to be input to the algorithm computing that function. So previously, when we talked about computing a real number, there was basically a natural number input. And remember that we can carry back and forth natural number as input, output a single approximation, or no input, output a sequence of approximations. And that's obviously the same, equivalent both mathematically via currying and computationally outputting a sequence of numbers or outputting any desired index of that sequence. And when we talked about computing a sequence, also there was only finite input. So natural number n can be encoded as a finite binary string. It's a finite object, and for sequences the same is true. Here we have two integers as input, the precision parameter n and the sequence index j, but both are natural numbers, they are finite. However, now we're talking about computing a real function where the input, where the argument is a real number, and real number is an infinite object, right? So how do we present an infinite object to the computation? And the idea, the solution, which goes back to actually Gregorczyk, is that the real number is also input in the very same way that the real value is output, namely by means of a sequence, infinite sequence of approximations which can be accessed, for instance, as oracles. So input is an infinite sequence of rational approximations up to error 2 to the minus n, or equivalently numerators, integer numerators, with denominators integer powers of 2, and output is the same type, same kind of way of outputting a real number. And the benefit, the nice thing about this definition is that it immediately yields closure under composition. Whenever f is a computable real function and g is a computable real function, then also the composition, first f then g, is a computable real function, because, well, because we can obviously interleave the computation, namely whenever the second computation of g requires some higher precision of input approximation, then we can resume the computation of f to produce such an approximation. So this is an important point that I'd like to emphasize again, namely computation now is of course an infinite process, right? It was already before here, outputting an infinite sequence. Same here, outputting an infinite sequence, but now that the input is also infinite, the computation cannot wait for the input to be, cannot first read the input before starting to produce the output, because the input is infinite. So the computation must start producing at least approximations to the value, while knowing only so far finite information, finite approximation to the argument, and then while producing better and better output approximation, then it can access and try to read better and better input approximation. So that's an important but subtle point with a definition. And that also is reflected when we formally prove that this notion is closed under composition. If we have a computation of a function g, then this will access better and better approximation to the argument to g, and if that argument to g is the value f of x of another function, then the computation that produces these better and better approximations must be kind of interleaved with the computation that computes the function g. This is maybe similar to the proof that, for instance, logarithmic space computation is closed under composition, which also involves such an interleaved execution of two computations. Okay, so, and another point that I've fortunately emphasized sufficiently well during our last lecture is that we deliberately do not define the behavior of the computation for arguments that lie outside of the domain, nor do we specify the behavior on when their input sequence of approximations are not consistent, for instance, with each other, to consistent with one single real argument. Then the computation can behave arbitrarily, and in particular, it is still allowed to output something, whatever, if it likes. And finally, let me emphasize that this definition of computing a real function is also, it's not restricted to computable arguments. It must work for any possible argument x, not necessarily only to computable arguments. There's a variant, another notion that only considers computable arguments given by codes of algorithms that compute the argument. So not by approximations, but by a code of the argument, and a code of a program, of course, is finite. So this alternative definition, it's called what is it called? Markov computability, that has finite input, namely the code of a program, of a while program, of a Turing machine that computes the argument x. And if we want a different argument x prime, then we need to input a different code of a different program. But these codes are only finite. So in this definition, there's only finite size input. They can be read in finite time, but the inputs are thereby implicitly restricted to computable arguments. There's no way to input a uncomputable real number, because these numbers do not have any algorithm that compute them. Here, and that has been established over the decades in computer analysis, it is beneficial. It has much nicer properties if we do not restrict only to computable arguments. That's one of the lessons learned from decades of investigation in computable analysis, and we follow that tradition here. And yes, as I said, this notion has nice properties, among them being nice closure properties. This is to convince maybe more numerical scientists than you attending my lecture that this is a reasonable definition, because the criticism comes on the next slide. So let's first recall the beneficial properties of that definitions, and recall that the hardest part in mathematics is to convey to propagate a new definition, a new notion, because proofs and theorems are usually in mathematics undisputed, but definitions are subject to dispute. And the good properties of this definition is that, for instance, computable sequences are mapped to computable sequences by computable functions. Computable functions are closed under composition, as I just mentioned, with this interleaved computation. And any restriction of a computable function is again computable, which is kind of trivially true because of this last property. We simply don't require any behavior outside of the domain. So if we have a computation and we restrict the domain, we can simply reuse the same computation to compute the restriction. Okay. And the criticism that I already mentioned comes now here, namely the fact that any computable function must necessarily be continuous, right? So let me again emphasize that there are other notions of computing real functions. There's a trade-off, right? Some scientists are not happy with this consequence that any computable function must be continuous, and therefore modify the definition. And we will see in a minute, once we have recalled the proof or proof sketch that any computable function must be continuous, how one could perhaps change the notion to include also discontinuous function. So recall the proof. It's a proof by contradiction. It's a proof by taking a hypothetical computation of a discontinuous function like this. And then we're going to conclude that this purported computation actually is incorrect. It makes mistakes. It produces wrong output on some argument. And the proof goes as follows. First, we run the hypothetical computation on the argument x, which is at the very point of discontinuity. And let me emphasize that the discontinuity could be an uncomputable argument, right? But remember, we have not excluded uncomputable arguments. So uncomputable arguments are still possible. So the computation must also work correctly on a possibly uncomputable argument at the discontinuity. And then we run the computation. Remember, the computation here for your convenience is the recall of the definition. Convert an infinite sequence of approximations of the argument to an infinite sequence of approximations to the value, right? And the sequence of approximation to the argument need not be in one-to-one correspondence to the elements, to the entries of the sequence of values, but both must eventually be infinite, unbounded. So when we run the computation on, let's say, this approximate argument, then maybe immediately or sooner or later an approximation to the value will be output, input beta approximation to the argument, beta approximation to the value, and so on, until eventually the output approximation, right, they have up to error 2 to the minus n. So for some sufficiently large n, after running this purported computation for a sufficient amount of time, eventually the error bound of the output approximation will be smaller than the width of the discontinuity. Could be a very small discontinuity, but it's non-zero. There's a jump, and so eventually the output approximation will be smaller than this jump. And now we're going to use that information. We are going to fool the purported computation to demonstrate, to show that this cannot work correctly always. It's the same way as we proved that the purported solution to the halting problem must eventually make an error. And then what we're going to do now is we're going to, this is like a thought experiment, we're going to restart the computative computation on a slightly perturbed argument x prime, which again may or may not be a computable real number, but which we choose in our proof by contradiction to be sufficiently close to the original argument so that all the finitely many input approximations apply to both of them. Right, let me emphasize that again. So the computation after a finite number of steps has produced an output approximation which is which excludes one of the two values at the discontinuity. It includes this one, but it excludes this one after a number of steps and after reaching a finite output position whose value we don't know, but which it exists. And therefore, until this point in time, the computation has been able to read, to access only a finite number of input approximation could read the argument, real argument x, only to finite precision, not exactly. And therefore, there's room kind of in this input approximation sequence where we're very close to the original argument, but distinct, different from the discontinuity where the value is significantly different. That's the point of a discontinuity. It is compatible. It can use the same input approximation finitely many, right? And that's what we're going to do here. We choose an argument x prime, which still lies in all these finitely many intervals that the purported computation has been able to read so far. And then we're going to restart the purported computation with this argument, reusing the finitely many input approximations. And after that, finitely many, of course, proceed differently with different arguments because eventually they must now converge to this x prime rather than to x. But since the computation is deterministic, it will again start by producing the same output approximation as previously because it is seeing, it reads the same input approximations. So it will behave in the same way, and in particular will output the same output approximation, including this yellow approximation, which, as you recall, we've chosen, we've simulated the computation for an amount of time such that this interval now excludes the actual value at the perturbed argument x prime, and therefore is an incorrect output approximation to the value f of x prime, which is a contradiction to the hypothesis, to the claim that the computation can compute this specific discontinuous function. And of course, this kind of argument generalizes to any kind of discontinuous function. Let me emphasize again, if the discontinuity happens at an uncomputable argument, then we really need here that our computation is supposed to be correct also for uncomputable arguments. But this is not what requires continuity. There's a also for this other notion of continuity, computability, Markov computability, it is true that any computable real function with reasonable domain must necessarily be continuous. So yes, and as I said, this is a point of contention to, for instance, in numerics, because it excludes many interesting functions. It excludes the sign, the signum function. The signum function is discontinuous and therefore uncomputable in this setting. The rank of a matrix, the rank function depends discontinuously on the matrix entries and therefore is also uncomputable. So this is a source or core of strong criticism of this notion of computing a real function. So let us briefly discuss alternative definitions and their advantages and disadvantages. So one popular alternative definition is to say that the argument is not be presented by an imprinted sequence of approximations, but the argument must be presented exactly, because this is basically the essence what results in the uncomputability of discontinuous functions. When we only know approximations, then we can never be sure in the computation what is the actual argument. Whereas if the argument is, the definition is such that the argument must be presented exactly, then one can compare, hopefully, this argument with 0 or any other fixed value to see whether we're past or below the discontinuity. But the disadvantage is, of course, how can we present arguments exactly, and which arguments, right? So, for instance, general real numbers, including transcendental numbers, have too much information. They're infinite information, and therefore cannot be presented or input within finite time, within finite information. So people often, therefore, or people have to restrict the type of arguments to be not arbitrary real numbers, but for instance only rational numbers, which, fair enough, can be presented exactly with numerator and denominator. But the disadvantage is, of course, rational numbers are first a serious restriction compared to real numbers. They have many disadvantages, and furthermore, this notion, this variant notion, violates close under composition, right? So when the input is supposed to be given as an exact rational number, then but the output is produced by infinite sequence of approximation, and these approximations cannot serve as input to a subsequent computation of a function g, because that would again require exact inputs and inputs restricted to rational numbers. So how can we maintain closure under composition? We could, for instance, change the definition such that also the output must be presented exactly, maybe again as a rational number. But then, of course, many important functions, transcendental functions such as the exponential function, elude computability because they map rational arguments to irrational arguments, right? To transcendental arguments. That's Lindemann-Weierstrass theorem. So the baseline here is we have many trade-offs when conceiving such a definition, and depending on what the priority, one can, for instance, one can change, and people have changed the definition so that also discontinuous functions can become computable, but then, for instance, the exponential function regularly becomes uncomputable. Or if the definition is made such that also the exponential function is computable, then closer under composition of computable function gets violated. So yeah, so there are many desirable properties for such a definition, but one probably cannot have all properties at the same time, and therefore, depending which of the properties you're willing to sacrifice, then that gives rise to different definitions with different properties. But in this lecture, after several decades of research and investigation in computable analysis, this is a definition that we will adopt in this lecture. Okay, so moving on. So now that we've come to terms with the fact that any computable real function must necessarily be continuous, recall the classical Weierstrass theorem, which says that any continuous function on a compact domain can be uniformly approximated by polynomials. Right? Let's say that again. Of course, every polynomial is continuous, right? And the uniform limit of continuous function, uniform in the supremum norm, is again continuous. So when we have a sequence of polynomials that converge uniformly, then their limit is again a continuous function, and the Weierstrass theorem says that the converse also holds. If we have a continuous function on a compact domain, important hypothesis, then there exists a sequence of polynomials which converges uniformly to that continuous function. So compactness here of the domain is a crucial property, and actually compactness will occur repeatedly again throughout this lecture. This is something that actually is also true in discrete computation, but there it is often overlooked because it is just it is in disguise. I mean, the discrete realm the subset is continuous. Let's say a subset of integers is compact if and only if it is finite. So generally speaking, whenever compactness occurs in a real computation, there is a counterpart to that hypothesis or the claim, the consequence of a theorem that asserts compactness in the real setting. There's a corresponding statement in the discrete realm, but it is kind of hidden or trivial because it just says or requires something to be finite. Okay, so that actually real computation in this sense offers new insights into discrete computation, namely that and when the finiteness hypothesis generalizes to compactness hypothesis. Right, and here, as we talk about the Weierstrass theorem, compactness of the domain is an important hypothesis because every continuous function on a compact domain, as you know, is of course uniformly continuous. So uniform continuity will also play an important role in this lecture in computability and later complexity theory of real functions. And so that's a classical Weierstrass theorem, function on a compact domain. In this slide, we're going to consider the domain of the real unit interval. Continuous function on the real unit interval is, or function on the real unit interval is continuous if and only if it is the uniform limit of a sequence of polynomials, and these polynomials can even be restricted to have rational coefficients or even more dyadic rationals as coefficients. And the counterpart, the computable counterpart is what we're talking about here. It's the computable Weierstrass theorem, and that says this gives a alternative characterization of our definition of what it means to compute a real function. Namely, it will say a function on let's say, unit interval is computable if and only if it can be approximated by a computable sequence of dyadic polynomials. So this is actually a nice and natural generalization to what it means to compute a single real number. Recall, so for a single real number to compute means to output a sequence of dyadic rational approximations up to error 2 to the minus n. So this is an output-only process, and similarly, one could reasonably define a function on the real unit interval to be computable if and only if it's possible to output a sequence of dyadic rational polynomials that approximate that function. And of course, any single dyadic rational number can be produced in finite time. It's just the numerator in binary. And similarly, a rational polynomial can also be output in finite time, namely it has a finite degree and therefore finite number of coefficients, which, since we're talking about dyadic rational numbers, in turn can be output in finite time, finitely many coefficients, so that this is the natural counterpart to what it means to compute a real number, namely output-only approximations. More generally, output approximations from a fixed, dense, countable set, right? So in the first case, for real numbers, the countable dense set are the dyadic rationals, and in the higher type, the case of continuous functions, the approximations are from the countable set of rational Weierstrass polynomials, which is again a countable set. So that's a kind of an alternative natural definition. And recall that also for real numbers, we had several natural definitions, and then we proved them equivalent. And this is similarly what the Computable Weierstrass theorem achieves and attains for real functions. It proves actually three natural definitions, alternative definitions to the one we've just seen, definitions for what it means to compute a real function to be equivalent and therefore reasonable. Okay, so here's the statement of the Computable Weierstrass theorem. The following three definitions for a real function on the unit interval to compute this function are actually equivalent. And the first definition is the one that we've already seen and used on the last slide, namely to compute a real function means to compute, to convert any sequence of approximations, dyadic rational approximations to the argument x, to a sequence of dyadic rational approximations to the value f of x, right? This is a definition that we have seen and used on the previous slide to conclude that any computable function must be continuous. Second, equivalent but fundamentally different definition is right. So for convenience, here is again the definition of what of the dyadic rationals, and the second equivalent condition for what it means to compute a real function is that already mentioned Weierstrass computation, namely only giving output approximation, not transforming input approximation to output approximation, but only producing a sequence from that fixed dense subset of Weierstrass polynomials that approximate the given function uniformly up to any given error. So there's an algorithm that prints a sequence of dyadic rational polynomials, one variable with dyadic rationals as coefficients that approximate the given function uniformly. Uniformly means in supremum norm, here infinity norm, up to error 2 to the minus n. Okay, so this is, as I said, the natural counterpart to the output-only definition of computing a real number, only that the rational approximations are here replaced by rational polynomial approximations. And let me say that for one time again. This is a transformation perspective of a real function, and this is a perspective of a function as a single static object, maybe its graph in the Cartesian product or something similar, and therefore outputting only approximation to that static object. In both are mathematically, of course, the same, and the Computable Weierstrass theorem says that they're also computably equivalent. Okay, and I've already also announced that there's going to be a third equivalent, but again, superficially different definition, and that's based on the observation, or to recall for you, that any continuous function, and we're only talking about continuous functions anyway here, right? Any continuous function is already totally defined by its values on a dense sequence, on a dense subset of the arguments, right? So here the function f originally is defined on the entire unit interval, but if we restrict that function to, let's say, all dyadic rationals, then the original function can be uniquely recovered from that, because of a continuous function is uniquely defined by its values on a dense subset, in this case, the dense subset of dyadic rational. And the subset of dyadic rational is a countable set, so we can kind of sort all dyadic rationals between 0 and 1 in, let's say, lexicographical order. first depending on the denominator, right? 2 to the 0, then 2 to the 1, 2 to the 2, and so on. And if two dyadic rationals have the same denominator, then we compare them based on their numerator, which are integers here, right? So put differently, we can sort, we can put a total order on the set of dyadic rationals from 0 to 1, and thus consider these dyadic rationals as a sequence, right? And yeah, I'll get to the modulus of continuity in a minute. So now we can consider the sequence of values of that function on that sequence of arguments, right? So here we have dyadic rationals between 0 and 1, sorted, ordered in some sense, and bijection to the natural numbers, and therefore this is a sequence of real numbers, right? Every value on such a dyadic rational argument is a real number, so that this is a real sequence, right? And we've already defined what it means to compute a real sequence. So this is a natural definition, and the third definition of what it could mean for a real function, continuous real function, to be computable, namely that the sequence of real numbers obtained by taking the function on the sequence of dyadic rational arguments, this is required to be a computable sequence. And as you recall, we already proved that any function that is computable in the sense A maps computable real sequences to computable real sequences. And this, of course, is a computable real sequence. So necessary condition, necessary consequence from this first definition A is that this sequence must be computable. But however, the converse is of course not true. And the reason is that having this condition does not imply any continuity of the function, right? Actually, we need to suppose that the function is continuous in order to have the uniqueness of the function on this dense subset. So, and what happens now to our continuity hypothesis? We need to strengthen this as well. Namely, we need the function to be computably continuous, not just qualitatively, but computably. And this is the second part of the definition C. What should it mean for a function to be computably continuous? And here's the definition, and we formulate that in terms of quantitative continuity, namely in terms of a modulus of continuity, a modulus of uniform continuity to be precise. So remember the epsilon delta definition of continuity of function on a metric space. For every epsilon, there exists a delta such that whenever x and y are sufficiently close, then f of x and f of y are also sufficiently close. And instead of epsilon and delta being arbitrary real or rational numbers, we here restrict to them to be powers of 2. And this is what gives rise to the notion of a modulus of continuity. This is, don't confuse this with another popular notion in classical calculus of a modulus of continuity to be a real function. Here, this is a function from natural numbers to natural numbers, which we call mu. And it says whenever the arguments are close enough, have distance at most 2 to the minus mu of n. So when mu is large, that means these two numbers are very close. Then also the values must be very close, namely 2 to the minus n. So this is what it means to be a modulus of continuity, mu, a function from natural numbers to natural numbers. And if we now extend that third definition, not only that the sequence of real numbers here must be computable, but also that the function must have a computable modulus of continuity, then this third notion is also turns out to be equivalent to the other two. So on the next slide, we will learn a little bit more about the intuition and what it means to have such a modulus of continuity and a computable modulus of continuity. But for now and here, also, by the way, the proof of this theorem is also postponed to the next lecture. This is a pretty involved proof, but for now, let's appreciate the statement, right? Again, we have a statement that says three superficially different notions of are actually equivalent reasonable notions, right? Every single notion is reasonable, but the computable Weierstrass theorem says they are equivalent, and therefore we have actually one reasonable notion, similar to the statement that all three notions of what it means for a single real number to be computable. We proved these also to be equivalent and therefore reasonable. Okay, so yes, as I said, the proof of equivalence of these three items is postponed. Here's a sketch of how the strategy, how we're going to prove that. But before that, let's have a little bit closer look at this notion of a modulus of continuity, because it's probably furthest away from what you have learned in calculus, where there's the definition of a modulus of continuity is slightly different, namely as a real function with focus on its behavior at zero. Here it's a function from natural numbers to natural numbers. So this is a slide about quantitative continuity and how this is captured with the modulus of continuity. So on the previous slide, we talked about modulus of continuity for real functions. And here we immediately generalize that to function between metric spaces. And let me also announce that modulus of continuity will later in this lecture again turn out to be very crucial and interesting when we talk about complexity rather than computability. And there, of course, complexity is a quantitative property, computability is a qualitative property, and similarly, continuity is a qualitative property, and quantitative continuity is captured naturally, as I'm going to demonstrate, by a modulus of continuity. So here's the generalized definition, generalizing the one from the previous slide. Let's fix two metric spaces, X and Y, with metrics D and E. And let's consider functions from X to Y. And the modulus of continuity of such a function is any mapping from natural numbers to natural numbers. Right, so this is generic, this is abstract spaces, this is specific natural numbers to natural numbers. With the following property, whenever two arguments are sufficiently close in the metric D, right? The metric D is that one on X. It's sufficiently close means distance at most 2 to the minus mu of n, where mu is really that modulus. Then the values are also close, namely closer than 2 to the minus n, where now proximity is measured in the metric E of the codomain. So yeah, this is kind of capturing from a logical perspective. It means skolemizing the epsilon delta definition. So epsilon delta definition means for every epsilon there exists a delta, and if we skolemize that, it means there's a function that maps epsilon to delta, right? Delta says how close we must be with the argument. And it is no loss of generality to restrict both epsilon and delta to be integer powers of 2, as we do here. And also, let me emphasize that this is maybe more accurately called a modulus of uniform continuity, because general epsilon delta continuity, the delta is allowed to depend on x, but here there's no dependence on x allowed. So maybe it's a better but longer term to call this a modulus of uniform continuity. So for because I'm lazy, I'm going to just call it modulus of continuity. And this is a reasonable object mathematically. For instance, as you recall, the composition of two continuous functions is again continuous. And similarly, we have a quantitative statement. If a first function has modulus of continuity mu, and a second function has modulus of continuity nu, then their composition again has modulus of continuity, the composition of the two moduli of continuity. So that's a quantitative strengthening of the statement that the compositions of two, let's say, uniformly continuous is again, let's say, uniformly continuous. And let me point out the subtlety here, namely the order of the composition here changes. So here we have first F, then G. To F corresponds modulus mu, to G corresponds modulus nu, but here the composition is the other way around, first nu and then mu. And if you prove that, the proof is very simple actually, then you realize why the order of composition has to be reverted here. Maybe I'll put that up as next homework assignment, one of the next. Okay, so how does that correspond to other notions of quantitative continuity that you are probably more familiar with from calculus? For instance, you know, Lipschitz continuity. Lipschitz continuity means that the distance between function values is at most a constant factor times the distance between arguments. And now it's easy to see, at least for bounded metric space, that's important for bounded metric spaces. Lipschitz continuous functions are precisely those functions that has a modulus of this form. Mu of n is at most n plus some fixed constant. Okay, so not constant factor in front of n, but a constant additive term. And that constant additive term, right? Remember, Lipschitz constant is usually called a factor, right? How large a factor of the values differ from the distance from the arguments. But this becomes here an additive constant because we're talking here about exponents here, and why we consider this and not, for instance, 1 over n, but 2 to the minus n, that again will be explained later in the course of this lecture. So this is all discussions about why do we choose these definitions over other maybe more popular or common definitions. So in numerics, 1 over error bound 1 over n is also a common definition, and we choose 2 to the minus n, but there's a very good reason, several good reasons for this definition. And the most important or difficult part I find in mathematics is the sociology of mathematics, namely convincing people of a definition. It's easy to convince people of theorems or proofs because everybody can verify correctness of a proof. Well, not everybody, but it can be verified. But the correctness of a definition, there's no such notion. So there's only the notion of a definition to be reasonable. And how can we convince someone of a definition to be reasonable? One strategy is to demonstrate closure properties. And here we follow another property strategy, namely that we can re-express classical notion that everybody knows in terms of this new notion of a modulus of continuity. Namely here Lipschitz continuity. The next notion that you're probably familiar with from calculus is Hölder continuity, right? And again, Hölder continuity means, if you recall, that the distance between f of x and f of x prime is at most a constant factor, that's like with Lipschitz, times the distance between x and x prime raised to some power, usually less than 1. For instance, typical example is the square root function, right? Square root function on 0, 1 is not Lipschitz continuous. It becomes very steep towards 0. But of course, it's, well, not very, it's still a very mild, well, it's not even a singularity, right? But it is Hölder continuous with exponent 1 over 2 because it's a square root function, right? And so indeed one can re-express Hölder continuity in terms of modulus of continuity, namely these are precisely those functions whose modulus of continuity is linearly bounded. So here it's n plus a constant, and here it's n times some constant factor. And this is this allows to recover, to re-express Hölder continuity, now using the new notion of a modulus of continuity. And here's an example of a function which does not have a polynomial modulus of continuity, right? So all these functions have linear modulus of continuity. The linear function with linear modulus of continuity are precisely the Hölder continuous ones on bounded domains. But here's an explicit example of a continuous function, uniformly continuous function from the unit interval to the unit interval that has no linear, that does not even have a polynomial modulus of continuity, but only an exponential one. Well, it must have a modulus of continuity because it's a continuous function of a compact domain, right? So here's the function x between 0 and 1 gets mapped to 1 over the natural logarithm of e, Euler's constant, divided by x. Okay, and it's, first of all, I'd like to point out that the right-hand side of the function seems to have a singularity when x is equal to 0, right? When x is equal to 0, then there's a division by 0 error. E divided by 0, that's undefined, right? But of course, since high school, you know the heuristic to say e divided by 0, that's plus infinity, right? That's not rigorous mathematics, but a pretty good heuristic. So let's just follow that heuristic so that we have the natural logarithm of plus infinity. What's the natural logarithm of plus infinity? Again, it's technically it's undefined, but using the heuristic, that should be infinity, right? So that we again have 1 divided by infinity, which again is undefined, but using the heuristics, that should be 0. So that rigorously speaking, it seems like a good idea to make this function really fully well-defined also on 0, to technically extend that continuously extend that function to 0 being mapped to 0. And I leave it to you to verify that this is indeed the unique continuous extension of this natively partial function, right? Because it's not really defined for when x is equal to 0, but it can be continuously extended and then constitutes a total function from the unit interval to the unit interval, continuous also at 0. All other arguments, it's obviously continuous as a composition of continuous function, right? But the behavior at 0, that's what makes this function interesting. And this is also depicted here in this plotting, right? So it's actually a pretty small subinterval from the whole unit interval, but this is where the interesting part happens, right? Namely towards 0. And as you can see here, this gets very, very steep, and actually even much steeper than the square root function. Only superficially this could be a square root function, but the square root function, remember, is Hölder continuous, but this function, that's the whole point, is not even Hölder continuous. It does not have a linear, it does not even have a polynomial modulus of continuity. And again, I leave it to you maybe as a homework to verify, to assert that rigorously this function has an exponential but no polynomial modulus of continuity, in particular at 0, a function from 0, 1 interval to the 0, 1 interval. Now, if we have a function from continuous function from 0, 1 interval to the 0, 1 interval, then we can, of course, iterate that function, right? We can apply that function a second time to again map this unit interval back to the unit interval. And that's the last item on this slide. Let me, a second. If we iterate this function, if we consider this function h composed with itself, then things get even worse, right? Namely, then it has a double exponential modulus. This follows from our closure property here, right? So imagine mu and nu to be both the exponential modulus here, right? It's the same function after all. Then the composition, according to our lemma, has the composition of exponential function with the exponential function, which is double exponential function. And so that's one direction. And the interesting part is that actually this is again best possible. The composition of H with itself has not even single exponential modulus. And so by repeatedly iterating this function with itself, one arrives at a hierarchy of many continuous functions, right? Infinite hierarchy of uniformly continuous functions from the unit interval to the unit interval, but their quantitative continuity property, their modulus of continuity, climbs up the hierarchy towers of the exponential function. So this slide is supposed to convey you with some intuition about this modulus of continuity that plays such a crucial role in our computable version of the Weierstrass theorem. And actually that also concludes, no, I'm wrong. There's another, one more slide of this section about computability of real functions, namely examples and counterexamples. Right, so here for your convenience is again repeated the one or first definition of what it means to compute a real function. And so the first property that I'd like to emphasize and mention again, that any computable function, if we restrict it, then it's again a computable function. We've already seen that. Here are some further non-trivial examples of computable functions, namely transcendental functions. That's why one of the reasons why we choose that definition of putting only approximations to the value rather than exact values. In this way, we can have such transcendental functions, that's the exponential function. I'm not going to prove that here. Maybe later today. Our time is limited. Here are some closer properties of computable functions, namely they're closed under indefinite integration and parametrized maximization. So here you see the Riemann integral because any such computable function is continuous, right? So we don't need all the hassles of Lebesgue integrals or whatever. And the statement says this is again a computable function of the upper integration bound. Again, I have to postpone the proof of that. And also the parametric maximum, taking the maximum of that function on arguments between 0 and x, where x is now a parameter, so that this is again a function, not just a single real number. And the statement says that this is again a computable function. Again, I'm going to prove that later using our statement about the modulus of continuity, using the various characterizations of computable real functions. And here's a very interesting operation on computable functions, namely gluing two computable functions together. So here we have, by hypothesis, a computable function from the negative unit interval and another computable function on the positive unit interval. And of course, we can glue them together to a function defined on the interval from -1 to +1. But in general, gluing these functions together, every single function is of course continuous because it's required to be computable. But gluing them together can result in a discontinuous function, which must necessarily be uncomputable. Recall that any computable function must be continuous. So we actually need to impose another hypothesis, namely that the two functions that we're gluing together at 0 must also coincide at 0. Now the interesting thing is that with this additional and obviously necessary condition that the two functions we glue together, then their gluing together, which is technically called their join, is indeed again computable. And why is this so interesting? Because the natural attempt to prove this fails, right? So how would you prove that naively? Well, you would take the two algorithms, the algorithm that computes F and the algorithm that computes G, and then combine them into a new algorithm that computes the join, the gluing together, as follows. So the new algorithm gets an argument and then checks whether the argument is negative or positive. If it's negative, then the algorithm invokes the computation of F. If it's positive, then it invokes the computation of G. But this naive algorithm, of course, misses the important and interesting case when the argument X is equal to 0, right? That works, the algorithm works when the argument is negative. That algorithm works when the argument is positive, but when the argument is equal to 0, remember, test for equality is undecidable. So our naive algorithm will fail, will not produce any output for an argument when an argument is equal to 0. It will only result in a partial function not properly glued together. So we need a more sophisticated algorithm. And indeed, such a more sophisticated algorithm can be designed. And it's most easy, I guess, or very simple to do that when we have a modulus of continuity, but let me postpone that until our next lecture because we're running out of time. I have only a few minutes left. Namely, the last item on this slide is about modifier. Now, you may have learned about modifiers, maybe in the course on functional analysis or partial differential equations. Modifier is a C infinity function, an infinitely often differentiable function with compact support, or differently, a function which vanishes outside of a bounded interval, in this case, the interval from -1 to +1. So here you see an explicit expression for arguments between -1 and +1, and otherwise the function value is identically 0 outside of this interval from -1 to +1. And the interesting thing about this is really what happens when t tends to the bounds of this interval, when t tends to ±1. Right? So when t tends to ±1, again, we have here singularity superficially, right? The denominator becomes 0. So something non-zero divided by 0, that's infinity, with a minus that becomes -infinity. Exponential function to -infinity, that's 0, using our heuristic. And now it takes effort to actually make that heuristic formal to prove that this function is not only continuous at plus and -1, but also continuously differentiable twice, 3 times, 4 times, infinitely often on these interval bounds. But this is something that you may or may not have learned in classical calculus. The interesting new perspective in this lecture is that this function is actually computable. And again, proving that requires some subtle considerations at these interval bounds, because again, as in the example with the join, with the pasting, gluing together operation, we cannot simply test whether the argument is greater or less to ±1. So yes, again, I'll have to postpone this formal reasoning and conclude today's lecture by recalling what we've learned and discussed about computability of real functions. Namely, we've seen 3 natural but very different definitions to be actually equivalent. One definition taking the perspective of a function as a transformation from real number arguments to real number arguments, where now in our definition the real number arguments and real number values are considered given by sequences, infinite sequence of approximations to arguments and to values. And an important property of computation is that in order to produce a finite output approximation, only finite input approximation can be known, not the entire infinite sequence of input approximation. And this gave rise to our proof, which fools any computation that claims to compute a discontinuous function, because the finite approximation actually allows us to fool such a purported computation if the function under consideration is discontinuous. So this first definition immediately implies that computable functions are continuous, and then we considered another reasonable definition based on output approximation only, namely output of Weierstrass polynomials, and that is actually indeed equivalent. And the third definition is that the function under consideration maps a arbitrary or even a very specific dense sequence, a sequence of dyadic rational in the unit interval, maps that to a computable sequence of real the values function, and all need a computable version of continuity, not just qualitative, but computable continuity. That's was our third definition, and all three of them are actually equivalent, which is an indication that they're reasonable. Then we discussed possible alternative definitions that avoid the disadvantage of restricting to continuous functions, but they all had other disadvantages. Then we discussed quantitative notions of continuity, namely these models of continuity, and how that allows us to recapture classical notions that you know from calculus, like Lipschitz and Hölder continuity. And we've constructed an explicit hierarchy of uniformly continuous functions with worse and worse moduli of continuity, climbing up a hierarchy of exponential towers. And finally, we've seen here on this slide examples of computable functions, counterexamples. Trivial counterexamples are easy to construct. Just take any discontinuous function. But these are all continuous functions, and it takes some effort to prove them computable, because the if algorithm that just tests the argument whether it's greater, equal, or less than 0 do not work here and here. Okay, so unfortunately, this has to be all for today. Thanks for your attention, and see you again in next week.